Okay, let me start then. So welcome everyone. I hope everyone had a good vacation despite the current situation. It's my great pleasure to introduce Andrew in a few minutes as our next speaker for our webinar. But before I do that, let me remind you, as always, a few simple rules. If you have any question, you have to type your question in the chat box below. And from time to time, I will interrupt Andrew and repeat the questions, and Andrew will reply to them. You should be muted, so don't try to speak. And near the end of the talk, I might stop interrupting Andrew, and we'll just wait for the end of the talk to let Andrew answer all of the questions. All right, and before another thing, we'll have a few seminars already scheduled for September and October. Please check the website. In particular, Maxime Vonneau on the 19th of September and François Caron on the 16th of September. And then quite a few people in October, like Chris Oss. So please check the website and make sure to register if you want to attend these talks. All right, so now I have an incredible task of introducing Andrew, a man who needs absolutely no introduction because he has, I guess, one of the most famous blogs in statistics, if not the most famous blog, which is very influential in statistics, Bayesian statistics, political sciences. Andrew also wrote several books which are quite influential, including this one, just to show you I'm not lying, they're already influential. You should have, like me, you should have his books in the bookshelf. So this is Bayesian Data Analysis, already the third edition, an excellent book that covers Bayesian modeling, Bayesian computation, everything you need to know, you need to learn about if you want to implement some form of Bayesian analysis. Andrew is also behind the Stan software, which is used a lot these days in Bayesian analysis. You should really check it out if you don't know already about Stan, etc., etc., etc. So Andrew is a very influential Bayesian. He has worked in many areas, but quite a lot in political science recently. Given the current cycle of news, he might have a few words to say about the forthcoming election or not, I don't know. But anyway, thanks a lot, Andrew, for accepting to give a talk in our seminar. It's a great honor to have you, and I'll let you have a metaphorical floor now.
Je parle jusqu'à quelle heure?
You have 50 minutes, starting now.
Je suis ravi de parler avec vous. Et si le coronavirus n'était pas arrivé, peut-être je serais ici debout avec vous. Mais no. I'll speak in English, but first I'll tell you a story, a Bayesian story about France, because when I worked in Paris several years ago, I had to go to meet the doctor, and for my work permit, and she was asking me different questions, and then she asked if I drank alcohol. And I said, well, I drink a glass of red wine a few days a week because my doctor said it was good for my heart. And she said, no, don't, you shouldn't do that. It's very bad for your liver. You should stop right away. And then I was surprised at first because my American doctor had told me to drink wine. And then this French doctor told me not to. It seemed to violate my preconceptions of the two countries. But then I realized that actually the doctors were being Bayesian. So when the French doctor heard, well, a report is given with error. So when she heard me say I drink a few glasses of wine a week, she knows that there's reporting error. And since she was in France, her prior was that I might be an alcoholic. And so when she integrated out her uncertainty about my response error with the prior, she came up with the posterior that it's highly likely that I'm an alcoholic. And so she wanted to tell me to drink less. So it was interesting being on the receiving end of Bayesian inference in that way. I want to tell you, I'm going to tell you a couple examples of recent projects I've been involved in and my struggles, and then talk a little bit about workflow, which was the title of the talk. I don't have 50 minutes about workflow to tell you in that we're still kind of grappling with what the principles are, but maybe I want to convince you that it's an important topic. So I'll begin with an example of the coronavirus. A few months ago, a team of researchers based at Stanford University conducted an opt-in survey in the surrounding county testing for coronavirus antibodies. The result was that 50 out of 3,000 people in the survey, 1.5%, tested positive. Extrapolating this to the population of the county as a whole yields an estimate of about 30,000 exposed, which was much larger than the number of confirmed positive cases at the time, because back in April, very few people had been tested. So everyone knew that the number of confirmed cases was much less than the total number of people exposed, but it wasn't clear how much lower. The Stanford study was posted on preprint server on April 11th, and its authors were soon writing op-eds and explaining their implications of their finding on national television. The key result from their preprint was that there were between 50 and 85 times as many cases as confirmed positive. Now, then 3 statistical questions arose from this. The first was, could we trust the results at all, given that the survey was not a random sample? The second was, I told you that 1.5% of the people in the survey tested positive, but in the report, the estimate that they gave was a range from 2.5 to 4.2%. So how did the raw rate of 1.5% jump up to 3 or 4% in the preprint? Third, where did their range of uncertainty come from? And is that range of uncertainty appropriate given sampling variability in the data? Now, the first 2 questions go together. Remember, the first 2 questions are the representativeness of the survey and how the raw rate got inflated in the report. The inflation of the raw rate came from a statistical adjustment that the authors did to correct for differences between sample and population. They corrected for sex, ethnicity, and postal code. Unfortunately, there are a few reasons we do not feel comfortable with these adjustments. First, they didn't adjust for age, which is kind of the #1 concern with coronavirus. Second, the adjustment for postal code is potentially very noisy because there are actually 58 postal codes in the county, which makes adjustment difficult given that the sample contained only 50 positive tests. Third, there was concern that even after demographic and geographic adjustment, people who were more at risk were more likely to get tested. And finally, that there are many researcher degrees of freedom in the adjustment process, leading us to be skeptical of any published result. So this is the sort of problem where Bayesian analysis excels, or should at least, that we have a small amount of data, we have a fair amount of prior information, and we're trying to propagate uncertainty from multiple data sources. So we wrote a model in Stan, and I'll tell you briefly what our kind of struggles with that. So the first model says we have a binomial distribution. We have some number of positive cases out of some number of tests. We allow for there to be an unknown specificity and sensitivity of the test. 100% specificity and sensitivity would be a perfect test. Otherwise, you can have misclassifications. This is important because when the underlying rate, when the rate is as low as 1.5%, even very low error rates can pollute your data. And there are many famous examples. Indeed, it's a standard problem. If there are like 5 standard examples in probability theory. One of those 5 examples is the example of the rare test, where the test of a rare disease, where even a small error rate can completely destroy the answer. So you need to account for that. In this preprint, they had data on prior tests, so that gives some evidence of sensitivity and specificity. So we put all that in the Bayesian model using our default flat priors, and it ran fine. And it gave the result, which you can also get using other approaches, that the data are actually consistent with 0 rates of exposure. We don't think there was a 0 rate of exposure, but the real point is that there was more uncertainty there was more uncertainty in the underlying rate than was captured using the classical analysis. And that's just kind of happens all the time, because non-Bayesian analyses often use plug-in values for different parameters. And when you have high uncertainty, that creates a problem. This is not to say that you can't do this in a non-Bayesian way, just that people tried and they failed. Paradoxically, the non-Bayesian classical approach, I think one reason why practitioners do it is because it seems simpler, but it's actually not simpler. It takes quite a bit of effort to do that right. So the next step was that various people, including me, pointed out that there was wide uncertainty deriving from uncertainty in the specificity and sensitivity, and so we needed more, and so we couldn't make strong conclusions from the data. So the researchers came back, and the uncertainty came because we only had a certain amount of prior data on the properties of the test. So they came back with more prior data on the properties of the test. Now, at this point, I should say it might sound funny to say they came back with more prior data, because obviously it came afterwards. That's not really a problem, though. Sometimes rather than using the term prior information, I prefer using the term external information. So it's a standard part of any statistical workflow that you make various simplifying assumptions, and then if your results are insufficiently precise, you go back and look for more data. So there's nothing wrong with that. Bayesian or non-Bayesian, this is often how we proceed, is we get some data, do some inferences, and then we gather more data. And the more data we gather can be from the past. It doesn't have to be future data. Anyway, they had several tests of specificity and sensitivity, several prior experiments that they put together, and putting them together, they claimed that they could have a very precise inference, but that was also mistaken because they weren't allowing for the fact that specificity and sensitivity could vary from study to study. So it's easy to write this model in Stan. You just expand it and you say that instead of specificity and sensitivity being fixed numbers, they have probability distributions, and you put in a hierarchical model, and you have a prior mean and you have a mean and a standard deviation for the specificity distribution and the sensitivity distribution. You estimate these from the data. So we did that, and this is where our first problem came. That our posterior intervals were too wide. We had remember I said it was 1.5% of the people in the study tested positive. Our posterior interval went from 0% to something like 25%. Well, how could you have 25% of the people be positive for coronavirus if only 1.5% actually tested positive? Well, only if the test has a very huge error rate. Well, we don't think the test has a huge error rate, but if you fit a hierarchical model and allow the sensitivity of the test to vary from study to study, there are only 3 prior studies. And so it's very hard to estimate the group level variance when you only have 3. So you need to put in actual prior information, and that's kind of a real thing. You have to say that we are assuming that the sensitivity can't vary by too much. But we put a strong prior on that, and then a stronger prior in the specificities. Then we move forward, and things worked out okay. But I wanted to share that example because it was relatively simple, but this kind of thing comes up a lot. You do the analysis and the results don't completely make sense. That means you have prior information that you haven't put in the model. And sometimes historically we've been kind of embarrassed to put prior information in, but in some sense you have to. Otherwise your model includes things that aren't realistic. Okay, so that's example number one. Example number two, Nicolas mentioned that we have an election in the United States coming up that some of you might have heard of. I was contacted a few months ago by a journalist at The Economist magazine, and they wanted to build an election forecasting model. And so we did so, and it included the following pieces of information. There are, well, the election's based on the 50 states. So there are state polls, there are national polls. We also have what's called a fundamentals-based election forecast. That's where you say that it's, we forecast that Donald Trump will get 46% of the vote, two-party vote in the election with quite a bit of uncertainty. That forecast comes from the fact that the economy is going poorly and he's an incumbent president with low popularity. We actually, the model is somewhat complicated and it allows for political polarization, meaning that in previous, we expect current elections to be closer than elections were 30 or 40 or 50 years ago because Americans are so polarized and don't usually change their partisanship no matter who's running. So we have four aspects of the model: state polls, national polls, fundamentals-based forecast, and a time series model for how public opinion changes between now and the election. Currently, we give Joe Biden something like a 90% chance of winning because he's at about 54% in the polls, and the fundamentals-based forecast is about 54%. There's not a large, there's no reason based on historical elections to expect huge swings between now and then. But we have some uncertainty. It's only 90%. It's not 100% because historically there have been such swings. Also, the fundamentals-based forecasts can be off by a few percentage points. And finally, polls have systematic errors. We put the model together. I'm not going to give you the detail. All the code it's the stand code and the R code's all online. It's all public, so you can look at it on your own time. But I'm just trying to emphasize like how we really consciously thought of the model as putting together a set of different pieces of information. That's how we thought about it. Not as we're modeling a single data set, but that we have this target that's kind of sitting in the middle and then a bunch of pieces of data like addressing it in different ways. And that's how we do applied statistics. But if you look at textbooks, it doesn't usually look that way, right? In textbooks, there's usually, wait a second. In textbooks, it's usually either here's the model and that's it, or here's the data and that's it. Not so much this kind of ongoing process. Now, the difficulty here arose because people looked at, we put our forecast on the web. I need to get a drink of water. Wait a moment. People looked at our forecast on the web and they found that they didn't completely believe it. So we had something like a 99% chance or 98% chance that Biden would win more votes than Trump. Now, it's kind of complicated. In the US system, you can win more votes and still lose the election. I won't go into the details. But we didn't completely feel comfortable with that 98 or 99%. And so we went back, we had to go back and look at the model and say, well, if we don't believe that, what aspect of the model don't we believe? Is it the fundamentals-based forecast that we don't believe? Am I showing slides? Someone wrote. No, I'm not showing slides. If I was showing slides, you'd see my slides, right? I don't like slides. It's good to visualize, right? It's good to be able to focus. So what aspect of the model didn't we believe? And we looked, we refactored our code. And for one thing, we had a bunch of bugs in our code. And so one lesson is if you put your, if you have your code in a major magazine and anyone can see it, people still won't look at your code and debug it for you. So we were kind of pushed to do that. We had some issues with the correlations between states. So I think the correlations of the error, our time series model for how the states could vary, how public opinion could vary over time allows it to vary by state, and it's correlated, and we kind of messed up in specifying the correlation matrix. So I think the correlations were a bit too low. So that was kind of not allowing the national error to be as large as it should have been. But interestingly enough, certain ideas that we had didn't work. So we thought we could do certain things like replace normal distributions with t distributions, and that would give us more uncertainty. But that really wasn't what was going on. So it took a bit of work to get to that. Okay. So now let me talk a little bit about workflow. Then we could maybe do a couple more examples to demonstrate. So let's start. Okay, when I was a student, there was this thing called, many years ago when I was a student, there was this thing called Bayesian Inference. And Bayesian Inference was like the thing in the statistics textbooks where you have data, you have a model, and you do some integrals. And that was it. Maybe there was something about choosing your prior distribution, certainly nothing about choosing your data model. Bayesian inference is just this kind of mathematical step. When we wrote our book, we expanded this to what we called Bayesian data analysis. And that included 3 steps: building a model, then inference, then checking and expanding the model. So in a way that's kind of obvious, but those other steps had not been formalized before. And I'm not saying that we did a great job of formalizing model building or model checking and model expansion in our book, but just that I think it was important that we recognize that they existed. So to me, a lot of the history of statistics is about people giving a name for something, recognizing that it's a struggle, and then working and trying to figure things out. So there are a lot of examples. Like, for example, exploratory data analysis. So that's just a word, that's just a phrase, but it's kind of taking data exploration and graphics and giving it a name. Well, so what? You give it a name. People made graphs before the phrase exploratory data analysis was invented, and people made graphs afterward. Well, the difference is if you look carefully at the work of Tukey and others on exploratory data analysis, you'll see that EDA is comparative. What I mean by that is the way Tukey put it is what you want is you look to see unexpected patterns in data. What does that mean? Unexpected patterns, that's patterns relative to expected patterns. So exploratory data analysis is not just graphing data, it's graphing data and comparing them to your preconceptions, to your model. So it's actually a form of model checking. And once you realize that, you realize that exploratory data analysis is not just this thing you do before you see your data in order to figure out what transformation to use. It's also a way of checking your model and a way of figuring out where your model needs expansion. Another example of the way that statistics, that naming things can make a difference is causal inference. So way back when, people didn't really think of causal inference as a formal part of statistics. And Rubin and others in the 70s and 80s and 90s put a lot of work into that. And now people do a better job of causal inference, partly because they recognize that there are specific issues of identification, which are distinct issues in statistics. Another example would be hierarchical models. So back in the 50s, people talked about empirical Bayes, which would be like, I want to do Bayesian inference, but I don't know my prior, so I need to estimate it from data. And it was this kind of weird non-Bayesian thing, like, because full Bayesian didn't work. But then when it was folded up into hierarchical modeling, multi-level modeling, now we can actually do full Bayesian inference and estimate priors from data. Although even now, we're still only gradually realizing the benefits of including stronger prior information. So people like me did a bad thing. So in our books, we emphasize the idea that you can fit a hierarchical model and estimate the hyperpriors from data. But I think we made the mistake, not just us, but we in particular also made this mistake of downplaying the role of real prior information. And if you have hundreds of groups, then yes, you can estimate the hyperprior from data and it's no problem. But when you have a small number of groups, this sort of prior information is very valuable. Anyway, that was a bit of a digression. But now so if we think of model building, if we think of Bayesian data analysis and we think of model building and model checking as actually tasks of the statistician, then we can attempt to formalize it. And then we can try to say, how do models get built? And they're built in a sort of language-like process. So a language like Stan actually allows you to build such a model, or languages like Bugs, for that matter. And then similarly with model checking, that if we know that this is part of what we're doing, part of data analysis, that we can think about it more seriously. So we went from Bayesian inference to Bayesian data analysis. That's like, it just changed what it meant to be a Bayesian. But then the next step is to go from Bayesian data analysis to Bayesian workflow. Now, what do I mean by that? Workflow so it's not just constructing a model, fitting a model, checking and expanding a model. There are other steps involved in workflow. And most importantly, what I want to focus on, what I think is the thing that's been missing from our theory and our textbooks, is the idea of comparing multiple models fit to the same data. Now, we do some of this. There's obviously work on Bayesian model averaging. Aki, Vettori, and other people have done a lot of work on cross-validation, Bayesian cross-validation for comparing models, using stacking to average models. That's all based on the idea that I have a bunch of models and either one of them is the right one and I want to find it, or I have a bunch of models and I want to put them together to create a good prediction. I'm talking about something different though. What I'm talking about is fitting a series of models, not for the purpose of choosing one or averaging over them, but as a part of the data analysis process. So an example would be that coronavirus study that I mentioned. We started with a simple model, then we added more information and added a hierarchical model. Then we weren't satisfied with it, and so we put in informative priors. Then we did some sensitivity analysis. Now, if you think about that, so let's say there's three models. To simplify here, let's say there's three models. There's our first model on the one local experiment. Then there's the hierarchical model with the flat priors. Then there's the hierarchical model with the informative priors. We don't fit these three models and then say, which do we want? Like, we know we want the third one. We built up to it. And we're not trying to average over them or figure out their posterior probabilities or anything else. However, the simpler models have a role, and there are two roles. So one is we kind of needed to build the simpler models to get to the more complicated models. So I think all of you, anyone who's ever analyzed data, has had to have this experience where you think you know the model you want to fit, and you write it all down, and then you work and figure out how to fit it, like how to get it to converge or whatever algorithm you're using. And then you finally fit it, and then you're like, okay, what do I do next? Does this even make sense? How do I think about this, right? You have a model with 1 million parameters. Then the hard part comes, right? I mean, unless you're if you're a bad scientist, you just stop, like you say, well, it fit, R hat's less than 1.1, I can publish. But if you're a good scientist, you realize that once you've got the thing to fit, then it's like, what do you do with it? Like, how do you know it makes sense? And the way we know it makes sense is that we compare it to simpler models. So we had the simpler model to start with. Then as we develop, we say, well, look what happened to this confidence interval, uncertainty interval. It became so wide. Why is that? What's happening? Similarly, with the election example, we had problems with our models. So then we fit another model. But then we keep fitting models and we keep comparing them and saying, well, wait, this model is different internally. How is it different externally? And that this is the part of workflow which I don't know, like, I don't feel like I can currently formulate it, but I want to write about it. And Tukey first wrote about exploratory data analysis in 1962. His book came out in 1977. As far as I'm concerned, it didn't get clearly formalized until 2003. In the sense that in 2003, I wrote a paper where I tried to connect it to model checking and posterior predictive checking. So anyway, I wouldn't have wanted Tukey to have waited until 2003 to write his paper just because he didn't have a theory of, right? So similarly, I think I want to talk about workflow. I think we need to be thinking about it even before we have a formal theory of it. And I want to make a meta statement about this, which is that I think of like there being a progression in sort of the statistics where we start with examples. And the first stage is like an example, you do something. The next stage is a case study. The case study is like an example where you very carefully figure out why you did each thing. Then the next step is a workflow, which is a kind of set of instructions or a path to take more generally. Then following workflow, you can have a method, which could like be programmed on the computer. And then after that, you can have a theory. You might actually be able to prove theoretical processes. And so I actually feel like, so if I can think about things like hierarchical modeling as having moved from individual examples of people doing hierarchical modeling toward case studies where people explain why they did it, toward workflows, which would be things like what was in Bayesian data analysis, toward algorithms and methods, such as in bugs and STAN, all the way to certain theory that people develop. Similarly, exploratory data analysis or causal inference, you can think of these as starting with appealing examples and moving toward trying to formalizing what makes these work. So I feel, yes.
Sorry to interrupt, but do you mind if I repeat one question we just got?
Of course.
It's from Sergio. Apart from model comparison, are there other open questions you find interesting in Bayesian workflow?
Well, first, let me just say, when I say model comparison, it means something slightly different than what people usually mean. Because usually when people say model comparison, they want to say which model is better. And I want to say model comparison, like I want to understand how things change as I move through model space. So yeah, there are other important issues beside model comparison, or however we want to call that. And another related but slightly different issue is model understanding. So sometimes people talk about explainable AI. In a Bayesian context, think about sensitivity. So the output is your inference, and the input are the data and the whatever like hyperparameters you have in your prior. And you can actually differentiate your posterior with respect to your data or your prior parameters. And you can do that in two different ways. So one way you can differentiate your posterior with respect to the data is to imagine the data changing a little bit, right? So literally differentiate the posterior with respect to the measurement. Another way that you can do it is what if your data are discrete? So if you have 0, 1 data, you can't differentiate a 0, 1 data point. There are two approaches you could do. One is you can do differencing. So you could say, how does my posterior change if I change a data point from 0 to 1 or 1 to 0? The other way is you can do this trick that Tamara Broderick and Michael Jordan and other people have worked on, which is to create a kind of pseudo likelihood where you take the contribution of that data point to the likelihood, and in the likelihood, that contribution is a power of 1. And if the data were excluded, it would have a power of 0, and you differentiate with respect to that power. So that's kind of an interesting idea also. A bunch of open questions here. One is just like how to incorporate that into a workflow, right? Like that is like the same way, just by analogy, think about something like R squared. Like there's a lot of work. I wrote a few papers on Bayesian R squared. There's a lot of work on that. But a big part of R squared is not just defining R squared. It's how does R squared fit into your workflow? What do you do with R squared, right? So similarly with this sensitivity, influence analysis or sensitivity analysis, part of it is how to do it. Another part is what do you do with it? I think it's super important. If you ever hear people talking about models, they'll say things like, well, we have this prediction, like let's say you're talking about these SEIR models of the coronavirus. And you say, well, it goes up and then it falls down and then it goes flat. And this last bit of curvature, or the last bit of curvature is coming from the data we have in certain countries where we have a long time series of data because it's a long lag. So actually, this part of the curve, you hear this all the time. This is a really important way of how we talk about statistics, right? This is super important, right? So we say, oh, the reason we know that is from this, or this, oh, this all comes from the prior, or oh, this curve, that's because we assume quadratic, so it has a quadratic shape. The data don't inform that at all. And you know that naive data analysts are often taking artifacts, which are basically just artifacts of the model, or weird data things, and taking them too seriously. So we want to be able to kind of talk back and forth. I have this idea of like a haptic controller. You can actually kind of grab the data, move the data around, and then see how the inferences change. But think about statistics textbooks, like to the extent we do that, we only do that in our examples. We don't have a formal method. You look at all my books, like Bayesian data analysis, you won't see us saying, like, how do you as a data analyst address this issue of influence? How do you think about what part of the curve is being estimated from what part of the data? So this is where like we need good examples and then good case studies, which can lead to the good workflow. We're not really there yet. Now, if we want to talk about open questions, a related open question is how to do this with higher structured data, like hierarchical data or time series or spatial data. If you have hierarchical data, or removing one data point isn't really the issue. You might really need to remove all the data for a certain patient. Or similarly with time series, taking one point out of the middle of the time series won't affect your inference much. That doesn't mean that point doesn't matter. It just means that you'd have to take out a whole chunk to do that. And we don't, part of the reason we don't have great methods for that is because we don't really have great ways of thinking about that, because we haven't been thinking about it formally. So I would argue that workflow itself is still in the early stages of being included in our thinking, but I think it's very important.
Andrew, we have two more questions in the meantime.
Okay.
The first one is from Shravan. The problem with fitting lots of Bayesian models is that it takes a huge amount of time to explore all these models. In practice, Andrew's proposal quickly becomes intractable. What is Andrew's experience with such a workflow?
Okay, so in practice, I do fit multiple models. So it's not like, okay, there's one thing that a good point, okay, there's something called the Folk theorem of statistical computing, which is that when you have problems with your computation, you often have problems with your model. Not always, some models are legitimately hard to fit, but often difficulty of fitting often corresponds to a lack of fit. Because if you have difficulty fitting, often that means you have like a weirdly curved posterior distribution, which represents that the data are consistent with that often it means that different parameter values are consistent with different values of the data. The folk theorem is important because bad models often take longer to fit. So it's a little bit like, you know, the scientific review process. A good paper gets 3 referee reports and it gets published in the top journal and it's done. A bad paper gets 15 referee reports. It gets 3 referee reports, it gets rejected, then it gets into the next journal, it gets 3 more, it gets rejected, then it gets into the next, so forth, right? So the scientific reviewing system is terrible because most effort goes into the worst papers. Similarly, with model fitting, a good fitting model, the model that you want, often doesn't take that long to fit once you know what you're doing. But some of the ones in the meantime take forever to fit. Paradoxically, a weakly specified model with very weak priors can actually take longer to fit because it's unconstrained and it gets lost in the big space. Or you can use some approximate method, but then the approximation will be way off. So one thing we need in our wish list of research is being able to fail fast. And that's something, again, if you look at the literature on statistical computation, including by me, there's very little on how to fail fast. Right? We tend to assume, if you look at the literature in statistical computing, almost all of what we write is assuming that we're trying to fit the model we want to fit. And how do you fit it well? If it takes too long, how do you approximate it? How do you diagnose problems and so forth? There's very little on the realistic fact that more than half the models we fit are wrong. I mean, they're not, I want to say wrong, they're all wrong. More than half the models we fit are not the models we want to fit, right? So to start with, we just have we have typos. So of course, the worst typos get caught in compilation. The model doesn't compile. But you can easily, as we did with our example of our election example, it's very easy to fit a model that seems reasonable, but still has big flaws. And we haven't thought that hard about that, like not wanting, but in practice this happens. Someone runs Stan at 2,000 iterations and it's not converging. And people are kind of naive and they'll say, like, we'll get messages on the help list. I ran it for 100,000 iterations and it took 2 weeks and still didn't converge. And I'm like, are you kidding? If it didn't converge, if it didn't come close after 100, like, I don't think 100,000 is usually a good idea. But people don't know that. They just think that's what they're supposed to do. So we're kind of falling down on the job on workflow. But again, part of the failure is we tend, in particular examples, we're always telling people, oh yeah, don't fit that model. That's a bad model. You messed up. It's not identified, so forth. But then if you look at like kind of the theory or what we usually write about, it's usually assuming that the model is what you're trying to fit. So yeah, that's not the only thing either. I mean, we're trying to write a paper with a lot of things, but that's part of it too. And there's also experimental design and data collection, and that's super important. I'm not really talking about that here, partly because that's one aspect of workflow that has been addressed pretty well in the literature. I mean, not perfectly, but people recognize that. Imagine what statistics would be like if people had never formalized experimental design, right?
Maybe let's take one more question and then let's leave the other question for the end of the talk, if you don't mind. So Leonidas asks, what is your opinion on the use of non-conjugate model in Bayesian inference?
Oh yeah, non-conjugate, fine. I mean, I'm kind of, I think there's 2 advantages of a conjugate model. One is that there can be computational advantages. So there's no reason in a small model it doesn't matter, but you can have a complicated model with a lot of data, and if it has parts of it that are conjugate, then you can integrate things out. So like in most of the time, I don't think about conjugacy at all, but it does come up sometimes when we are thinking hard about computation. And of course, Nicolas worked a lot on approximate algorithms and approximate integration and so forth. So he can tell you all about that. The other reason for conjugate models is that because there's closed form math, it can give us intuition. So when I'm explaining, we're learning about Bayesian inference, it makes sense to talk about normal models, because then we can see directly the partial pooling. Now, another kind of task of workflow, as I said, had to do with model understanding, right? What is the model doing? So if you have a non-conjugate model, you should be able to use computation to reproduce the intuition that you would get in a conjugate model, right? So for example, what if I have a simple conjugate statement that I have a fundamentals-based model of the election. Here's my prior mean and my prior standard deviation. It's normally distributed. And now I have a poll, and my poll has an estimate and the standard error associated with it. And then I also have an independent error, because the poll itself can have non-sampling error. So I have 3 sources of error, and I can do weighting and partial pooling, and I can see how it all works. Now, let's suppose I change things and say, well, they're no longer normally distributed, either because I want to use a different distribution, or more realistically, because I don't really have these direct data points. Like it's all kind of indirect within my computational framework. How can I summarize the partial pooling? So you can, I mean, we wrote a paper years ago where you can come up with a number for how much partial pooling you're doing without having to do the conjugate math. So I think that my answer to the conjugacy thing, I mean, it would have been very easy for me to just say, I don't care about conjugacy anymore. That's like yesterday's problem. But there are computational reasons. But again, I'm very interested in being able to understand our models better, to have conversations with our models. And so we should be able to do that in a non-conjugate model as well.
Okay, let's proceed if you don't mind. We leave you have a question for the end of the talk.
Well, maybe I should stop and just, it's already 11:50. So maybe it makes sense for me to just like answer other questions rather than, you know,
okay, as you wish.
I mean, I could do another example if you want to see one. You tell me.
Please make one more example, and then we'll take the question then, if you want.
Okay. So here, I will share the screen here. I have 2 examples I had prepared, so I'll show you one of them. Okay, share screen. Okay, now I'm sharing it, and now let me, okay, so you're seeing, are you
It
seeing
works
my
fine,
screen?
perfect.
Yeah, okay. So this is an example that came up wait, it's clicking all by itself. Pause share. Okay. Wait, now it's like moving, it's gonna start moving. Sorry, I have to figure out why it's doing that. Sure, let's do this. Okay. Okay, so, this is an example that I knew about because I was a physics student way back when. This is a well-known difficult problem in numerical analysis, and it's to estimate the sum of declining exponentials. And so it's a 4-parameter model, or I guess it's a 4-parameter deterministic model. So y equals a1 e to the minus b1 x plus a2 e to the minus b2x. It's well known that this is an ill-posed problem, much harder to solve than linear regression, even though there are only 4 parameters. Now the statistical, I'm going to demonstrate with a particular example. So this is the curve we're trying to discover. 1 e to the minus 0.1x plus 0.8 e to the minus 2x. If you look at the curve, it kind of, if you look carefully, it's not quite a declining exponential. It's like a declining exponential and then another declining exponential. So that kind of elbow in the curve is what allows you to estimate all 4 parameters. Well, I'm going to estimate it from noisy data. Sorry. So I assume that the true curve and simulated data, and then I fit the model with multiplicative error. So here's the stand code. You can kind of ignore everything till the end. The predicted data is a1 e to the minus b1x plus a2 e to the minus b2x. We're at the bottom here. And then we have a log normal model, because I'm just assuming that. The only tricky thing at all here is there's non-identifiability, because you can't know which component is which. So if you see I declared B to be ordered, So therefore, it identifies which component is which. And here it is. I simulated the data, and I just created fake data in R. This is the R code. Then I'm going to fit it. I fit the model in Stan, remember the true values, and it estimates everything fine. So the parameters A are 1 and 0.8, and here the estimates are 1 and 0.7, but there's a bit of uncertainty. Parameters B are 0.1 and 2, and they're estimated at 0.1 and 1.7, but again, with some uncertainty, 2's in the 95% interval. It worked fine. It was very pleasant. You just push a button and it worked. So now I'm going to try it again with some new parameter values. So before, the parameters B are the important parameters because they were the slopes, the coefficients of the declining exponentials. Before they were 0.1 and 2, and now I've made it 0.1 and 0.2. So now it's harder, right? Because they're closer to each other. Now I'll just say, well, okay, obviously if you look at the Stan output, it was a terrible fit. I was surprised. I mean, my intuition, I knew it's an ill-posed problem, but first, 0.1 and 0.2, they differ by a factor of 2. So shouldn't be that hard. Also, I did simulate 1,000 data points. So I was surprised it didn't fit. It had a horrible time fitting. B2 could be estimated to be as high as infinity. So infinity in this case means a declining exponential that just drops off immediately. What went wrong? So this is my curve, the true curve. I played around a little bit. It's pretty funny. I played around a little bit, and it turns out you can approximate on this range from 0 to 10, you can approximate this curve very well with a single declining exponential. So of course, given that, there's almost complete non-identifiability. You'd need more than 1,000 data points to tell the difference between the red line and the black line. And there's nothing special about the red line. Like once you have this, any line that's this plus any amount, like there's going to be an infinite number of curves that are very close to this. So you have terrible identification, which now I can see, but like I just wouldn't have known, right? I then throw in an informative prior. So my new default in life is to use normal 0-1 prior in everything. Now you might say that's ridiculous. Like what if you use normal 0-1 prior on my weight, and I say 0 kilograms with a standard deviation of 1. That'll be wrong. I weigh a lot more than a kilogram. Well, I would say you should be parameterizing things on dimensionless scales. So actually, a normal 0-1 prior on my weight wouldn't be so horrible if you were to have my weight relative to an average man's weight. Actually, it would be fine if you were to standardize me that way. In this case, I'm just kind of brute forcing it. I'm saying, well, the parameters, I think the parameters should be of order 1. I don't expect, I wouldn't apply this prior if I thought the parameters were going to take on values like 0.001 or 10,000. This is my kind of default prior when things are on unit scale. And then things work much better. Now, let me emphasize they're not perfect. So if my inference for B2, so my inference for B2, it's supposed to be 0.2. And yet my estimate's 1.9 with this very wide uncertainty. So it's not magic. And the convergence isn't great. It's still having difficulty mixing. But you can run it longer and it will converge better. But it's not like this prior doesn't solve the problem, except that it cuts away some of the worst examples. And so certain examples like this gave me a realization that they made this sort of example made me realize a few things. So first, like informative prior is no longer my last resort. Right? So even in a kind of generic problem like this, I'll basically say this is an unsolvable problem in general, but it's not unsolvable if I'm willing to bound or give a soft bound to the parameter values, and I should be able to do that. So it's kind of changed a bit how I've thought about statistics. And I've learned that from a few examples of that sort. It's kind of amazing how much we can learn from individual examples, as long as we're willing to, right? So I can only learn from that example because I will expand my framework, and I'm allowing myself to think about things like adding priors as part of my workflow in a way that, again, if you look at BDA, we weren't really doing that. I don't think we have any examples of BDA where we fit the model and we're having issues with it. And then we say, well, maybe there's prior information we're not using, or maybe we have to constrain the problem. Because that wasn't in our toolbox, like when we would have problems like this, we just, traditionally, I would have classified this as, oh, I shouldn't fit this model, which isn't really the right answer. So let me stop having done that example, and you did get to see a couple slides, so you got your money's worth in that way.
Thanks a lot, Andrew. That was super interesting. Let's go to a question. Sergio asked a very interesting question. Zubin Karamani said in a machine learning summer school that Bayesian belongs in the algorithm category, not in the model category. Can you comment on that? And its possible relation to workflow?
Oh yeah, well, Bayes is not a model, right? Like the model would be the declining exponential and the normal errors and whatever. Bayes is a way of combining information. So sure, Bayesianism is a framework. It allows you to, it's a framework which allows you to put in models and data and get inference, but it's not itself a model. It's like a language, right? It's not content. It's form.
So next question from Matthias. This is a discussion, so it's fine if we skip it. But regarding the model in The Economist, since Trump is arguably an unconventional politician running an unconventional campaign, what might suppose that historic patterns might no longer hold? Is there any Bayesian way to mitigate this kind of generalization change point problem without a causal theory or voting behavior?
First, I'll give a general answer, and then I will talk about the election. So my general answer is yes, there is a way of doing this. And the way of doing this is to say that I have parameter, like you'd say, I was going to fit a model with a certain parameter, like call it alpha. But now I'm concerned that there might be a change. The world is changing. So I'm going to allow alpha to vary over time. Or I'm going to say I have alpha from past data, and then for my new data, I have alpha prime. And I would put a prior on the difference, like alpha minus alpha prime. I don't think alpha prime is completely different from alpha, but it could be somewhat different. So we did this, Sebastian Weber and others at Novartis. We did this a few years ago in a model of drugs, and we had data from one drug, and then we wanted to combine with new data from a similar drug, but not quite the same. So instead of saying the new parameter was identical or exactly the same or completely different, we allowed there to be a prior for how much it differed. And I think this comes up a lot. Sometimes in computer science, they talk about transportability, which is this problem of can you transport inference from one scenario to another? And I keep saying you should just do this with a hierarchical model. So that's the general answer. For the election, we didn't really do that, except, so one thing, as I'll say, just about every presidential election is unusual in some way. So 2016 was unusual too, like it had a non-politician running for president. 2000 and the first female candidate. 2008 had the first non-white candidate. 1960 had the first Catholic candidate. There are many, 1992 and 1968 had major third-party candidates. So in some sense, the quick answer is that what you're asking is in the error term of the forecasting model. Now, I don't think 2020 will be particularly different in terms of swings of public opinion, and I don't think it'll be particularly different in terms of the polls. But so I think the vulnerability has to do with the fundamentals-based model. So in some way, what we're saying is, look, sure, like people have made this argument, like the economy isn't going well, but it's kind of a special case, so maybe it doesn't count as much. ultimately it's in the error term of the model. And then ultimately this gets back to model understanding. Like you want to say, well, Biden's at 54% of the polls and his fundamentals-based forecast is 54%. So there you are. If you want to say the fundamentals-based forecast should be 52%, then you'll get a slightly different, not much different, but a slightly different forecast. In some ways, this is one of the easier elections to forecast because the polls have been so stable during the past several months.
Thanks. Next question from Wei. Reasonable models often differ categorically across multiple dimensions. For instance, a component in or out, one of the model distributional assumption. What MATLAB often does is factorial model comparison, where every possible combination of ingredients constitutes a model. It makes the results harder to interpret, but it aspires to reduce modular bias. Is this a legit practice?
It's going to depend. So part of it, as the earlier comment came up, like you can end up with computational problems. And this is a little different from what I was talking about. Like, so we're kind of assuming you've gone past the finding bugs in your code and all that. So these are all somehow legitimate models. What I would like to do, I've thought about this for many years, and usually in this setting, what I would like to do is fit something more like a single model, including all the factors with partial pooling. So instead of either including a variable or excluding it, I would include it, but I would put in a strong prior on the variable. Now, there is, so Aki has actually done some work on this. Sometimes for computational reasons, you can't do that. So if I have 100 variables, I can't fit 2 to 100 possible models. And so you'd say, well, that's fine. I fit one model with all 100 variables, but that can be expensive. Like you can maybe once fit a model with 100 variables, but going forward, you don't necessarily want to waste your time on all 100 if most of them don't matter. So there's a research area having to do with taking a model and simplifying it, not because you think the simple model should make better predictions, but because it will reduce your cost in the future. And my request to you, if you're going to do that, is to think of this, like separate the problems of modeling, prediction, and future use. So like, I don't like when people say, well, I prefer the simpler model because it gives better predictions. There's a wonderful quote by Radford Neal in his PhD thesis saying that if you have a simpler model that gives better predictions than a more complicated model, then your problem is that you're sorry about this phone thing. Then if you have a simpler model that makes better predictions than the more complicated model, then the problem is your more complicated model is too weak. Because often when people say it's a more complicated model, what they mean is they included another parameter with a flat prior. But you shouldn't really be doing that, right? So like that, there's like in some sense that's evidence that there's a problem with that more complicated model. So if I didn't have computational constraints, I think we should fit the big model, and the little models are only there to help us understand things. On the other hand, for computational reasons you might want to avoid that, that's fine. And then I think you should think more carefully about what your costs are.
Okay, thanks. Next question by Sergio. In your opinion, should decision-making be part of the Bayesian workflow? If so, in which way can we include the choice of utility function in the workflow?
I think decision-making, and for that matter, experimental design, definitely should be part of the workflow. I haven't really talked about them because in some way I think we can decouple it. So we can talk about an inferential workflow without thinking too much about decision-making. Decision-making is always in the back of your mind because they're like Bayesian. There's a saying about Bayes, which I think you've heard, with great power comes great responsibility, right? So Bayesian inference will give you predictions about everything. And if you look at any Bayesian inference hard enough, you'll find some really stupid predictions. But usually they're things that you don't care about, so you don't worry about it. So knowing, at least informally, knowing what decision we're going to make informs our Bayesian modeling. when should that be formal? It kind of depends. I mean, I usually throw it back to people. Like if I'm doing data analysis and inference, I don't think too much about decision making, although I like to be a little aware of what the goals are. But then sometimes people come back to me and say, well, I'm using this threshold. I'm thresholding my p-values because we need to make real decisions. At that point, I'll throw it back in their face and say, well, oh, we need to make real decisions. What are your real decisions? What are your costs and benefits, right? If you're doing A/B testing or whatever it is, I do think it makes sense to formalize that. So yeah, once the decision comes in, I do think it's a good idea. Right now, I feel like we have enough on our plate just understanding Bayesian workflow at the inferential level, so I haven't thought that much about the decisions.
So next question from Mirail. You were describing your works on Bayesian workflow in terms of formalizing. What do you think about the opposite way, deformalizing, that is bringing more philosophy into statistics?
I don't know. I mean, philosophy is fine. You know, I say, like I wrote about this with Christian Hennig, that like philosophy is important for two reasons. One is a clear philosophy can maybe help you do better, right? Like, for example, thinking about models as being checkable can help you like design better model checks and do better inference. The other reason why philosophy is important is you can't really avoid philosophy. So there's no vacuum, right? If people who think that they're avoiding philosophy are just probably using some available philosophy and not reflecting upon it. So back in the old days, Bayesians had this subjectivist philosophy and they would refuse to check their models. And so bad philosophy was really getting in their way. So yeah, I mean, I think philosophy is important, and I think it is good to try to like reflect upon what are the philosophical foundations. I want to say one other thing, because this is related. This is based on this idea that when someone says they're just doing blah, 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 they're really doing something different. So an example would be, what if somebody says to me, I don't like your election modeling. I think things are changing a lot. 2020 is special. So therefore, I think the election's more like 50-50. Either candidate could win. So then I say, oh, why are you saying 50-50? Where did that come from? What I think then is people are weighting 2016 too much. So when someone says, I don't believe your model, what they're really often doing is using a model of their own and not formalizing it. So we have people say, like, where did 50-50 come from? Oh, well, 2016. So they're like, on one hand, they're saying that everything is different. On the other hand, they're saying they're going to make a big inference based on n=1. And that doesn't make sense to me. So it's very important to try to interrogate where our inferences come from. And one of Janes talked about this, E.T. Janes, that one of the most valuable aspects of Bayesian inference is that it creates a kind of paper trail from your assumptions and your data to your conclusions. So it forces me to be open about where my inferences are coming from. And then if you don't like my conclusions, then you can see what went wrong with my assumptions. And that's valuable for me. Like even in that simple fake data example with the declining exponentials, the problem was my original assumption that the parameters could be anywhere in the real line or in the positive real line. Once I realized that assumption was too strong, then I could do better.
Next question from Ching. If you have expertise within a certain domain, how do you advise incorporating the knowledge into priors?
I recommend, we have a prior choice wiki, so you could look at that, like if you Google prior choice wiki. But I would say first that I would try to put my parameters on a dimensionless scale. So rather than saying a certain parameter has like this prior based on like in units of centimeters or whatever, I would scale things based on some baseline of some sort. And then, so the advantage of that is it kind of forces me to take seriously what my baseline is. And the baseline, sometimes the baseline can be simple, like the average of the data. Other times you can do something different. Sometimes I feel like just setting up a prior can be biting off more than you can chew at once. If you decompose it into first setting up a scale and then saying, well, given this scaling factor, where do I think it is? Do I think it's higher or lower than the baseline? How much higher or lower? How uncertain will it be? Like that. That's one approach. The other way that you can incorporate this knowledge is to look at your inferences and say, well, do they make sense? And if you have an inference that doesn't make sense, that means it conflicts with some piece of understanding you have.
Next question from Sebastian. Comparing a supposedly true model to a simpler one, what do you expect to see on the inferred posteriors and the parameters? My guess is that fitting the wrong model would push a lot of uncertainty to the posterior of the parameters. But when you hit the right model, suddenly these posteriors are narrower. Do you agree? This sudden narrowing of the posteriors could be a sign that the model is correct.
I'm not sure. I would recommend that you explore this with some fake data simulation and some examples. So maybe you're onto something there. It's going to depend. I mean, one thing that we talk about is, it's not in our book. I always talk about when I teach, but I don't think it made its way into BDA, is comparing the normal model to the T model. So there's this funny thing. Suppose I have a parameter theta and it's let's say normal 0, 1. And then I have data and I have a measurement, which is y normal theta comma 1. So I have a measurement of standard deviation 1. My prior is normal 0, 1, and I get a measurement of 10. Well, then my posterior is normal with mean 5, standard deviation 1 over square root of 2. It's right in between. And it's somehow horrible because my posterior is inconsistent with the data and the prior. If I were to use T models, then you would end up with a bimodal posterior. So the point is that the normal model in this particular example has this property, a kind of unpleasant property that it doesn't adapt to the model not fitting the data. The T model has a more pleasant property that when the model starts not fitting the data, you get this kind of disagreement in there. But like, and we can easily understand mathematically why that is, because it has to do with the tails. But like, how do we think about that philosophically, as it were? Like, is there a class of Bayesian models that is like robust in that way? Like, if we talk about that being a robust, model under certain assumptions, like if you fit the T and the underlying thing is normal, it's not so bad. But if you fit the normal and the underlying thing is a T, it can be worse. So there's kind of stuff on robustness, but then when we're actually building models, it's not always clear how to check all that and how to put all that in.
Next question is a short one. Will you write a book formalizing the Bayesian workflow?
Oh yeah, we are. We have a contract for a book called Bayesian Workflow using Stan, because we felt that we kept putting too much stuff into the Stan Users Guide. We wrote a bunch. I wrote a bunch of chapters of this book about a year ago. And then other people got involved. So like lots of people wanted to do stuff, but then nobody was doing anything. Like we're still like, so we decided to write an article about it first because there's so many things that could be thrown into the book. But we did want to have this book because it's supposed to give like useful tips, something different. BDA is more theory, and then we have a bunch of case studies. We wanted something in between. So we are working on it. It's on our list of books to write.
Okay, maybe one last question because it's been quite a long time already. From Ron, is the difference between simple models and complex models in their ability to generalize? Is moving from one to the other improves your ability at this?
I'm not sure. Like I like to think of the complex model as the real model and the simple model as a way of understanding the complex model. So, I mean, an example, like what happens is often when the complex model is harder to fit, you realize it's because the simple model made a very strong assumption. So in that coronavirus example, we could fit the simple model very easily and it gave reasonable results. Then when we added data and we fit the hierarchical model, it didn't work and we needed to add the prior. But then if you think about it, the simple model was assuming, remember we added a prior because our complex model first failed because it allowed the specificity and sensitivity to vary too much between experiments. The simple model, we basically assumed the specificity and sensitivity were constants. So implicitly we had been fitting a model where sigma is 0. And then we allowed it to vary. So that's kind of often the case. Like I have an experiment and I do an analysis and it's very easy now, but now I have 3 experiments. And so now I fit a hierarchical model and it's really hard to fit. But why is it so hard to fit? Because we're actually like asking a more interesting question. So when the simple model works, I guess that's basically what the question was, that when the simple model works, often it's, quote, working because it's asking a very narrow question, but it's being interpreted more generally. So think of all the scientific papers where people do an experiment on 100 volunteers and then they say, this is what we know about human beings. That's a little bit silly, but they haven't formally tried to think about these extensions.
Thanks a lot, Andrew. Sorry, everyone. I see there's still a few questions left and maybe in the chat too. But I guess at some point I have to stop because otherwise the YouTube video is going far too long. Thanks a lot, Andrew. Yes, sir.
Merci une autre fois pour l'opportunité de parler avec vous.
Thanks a lot, Andrew. Merci beaucoup. Let's clap, Andrew.
Thank you. This is great.
Bonne soirée.
Bonsoir. Goodbye.